necessary. Now, the original idea I had in mind was airform construction, just a simple inflatable airform. It is used on Earth to build concrete domes, so it's a tried and proven method. The airforms are also reusable and very versatile. The way this works is you lay your foundation, set up the airform on the foundation, and inflate it to about 10 millibars or so internal pressure, and just lay the concrete on the outside. That's why we require low slump concrete, so it stays in place once it's put there. And the airform for the reference structure I've been working on, about 36 feet diameter, 36 feet high, similar to this shape. That airform would weigh around 350 pounds. And as I said, it's reusable. Lightweight, reusable, very flexible construction. You can put openings wherever you need them. And they're already used on Earth in remote regions with no local infrastructure, as you can see here. I think this picture was taken somewhere in Central America, either Guatemala or El Salvador. And now here's an example of the kind of construction I would be looking at. It would have to be buried in regolith, so what I'm looking at is you excavate location, you end up with something like that, and the structure itself would be at the bottom of that. Lay your foundation, set up your airform on there, and you lay out the concrete in successive rings going around. Let it set for several hours, lay your next ring, and so on. Build it up like that. Fill it in partially so you have a work surface there where you're laying your concrete. Build it up higher. You'd end up with something like that. And now, one thing that's been asked is, could it be used to seal up caves and lava tubes? Yes, it can. I've found it does have very good bonding strength to a lot of different materials, rocks and minerals. In all my testing, I haven't seen any bonding failure. All of the failure has been aggregate failure in my testing. I haven't seen any bonding failure where the aggregate separates from the cement. So the bonding strength is very good. Here are some pictures from the high rise. This is a cave they found, or some kind of a sinkhole. This picture was taken in infrared to see what was in the shadow there. And so we have caves there. Now, I was looking at a potential site, and I had another idea for construction that could be even more efficient. This is a high-rise image taken at a resolution of 25 centimeters per pixel. So we've got plenty of good-sized rocks and boulders strewn all over the place. This picture was taken a few weeks ago when my father and I visited a mining claim that my grandfather had on the Kern River up in the mountains back in the 60s and 70s. One of his friends actually lived in a little shelter he set up between those two boulders. And I got to thinking, well, if you have a few boulders there, you can just patch it in there, build a little shelter in there. This is a house in Portugal made by a method like that. It's nestled in between three huge boulders. The space in between filled in with smaller rocks cemented together. And we've used this kind of stone construction for centuries. That's also a possibility on Mars that would use much less materials. There's been a lot of talk about manufacturing bricks on Mars with sintered basalt or other materials, which would require a huge amount of energy, but really there's no point. Just use rocks like that, cement them together. And I still have a lot of work to do on this before it's ready for showtime. refining different mix designs for desired properties. I need to test compatibility with different materials because of the chloride and sulfate content. There would be corrosion problems with a lot of metals, so that would have to be solved. Long-term durability testing. Now, one issue with concrete, eventually it cracks. It's a form of rock. Any kind of rock under stress is going to eventually crack. If it starts cracking after 2 years, we have a problem. But if it goes for 20 or 50 years without cracking, then we have a viable construction material. And of course, the production methods have to be worked out. We have to develop equipment to produce the stuff that we can take to Mars. And if we end up we can't, of course, send a conventional concrete plant there. We have to have something we can pack into a capsule and send there, lightweight. And eventually we're going to have to build a full-scale prototype here on Earth, prototype habitat on Earth, and do testing on that over a period of a few years at least. And that's the work that needs to be done. And I got some assistance from Ron Voigt of a company called Forever Board that's using this material to make cement wall boards. So this stuff does have applications on Earth, has had for over a century. And Mark Shand from Premier Chemical gave me some technical advice on that. And I was hoping to have some questions, but to keep on schedule, I'm going to cut it short here. I'm going to be here through Monday, so if anybody wants to talk to me about it, I'll be here and I will be available throughout the weekend. Thank you.
Sets?
Yeah, yeah.
Okay.
And, okay.
Is it on this one?
Yeah, I copied it over. What were you gonna